underneath the reactions. Those are the reactions. This information was posted May 6th, but I also went over this when we talked about the periodic table and periodic trends. In fact, 3 or 4 of you actually presented the charges, the trends in charges. So that goes back more than 3 weeks or whatever. Using those charges to predict the formula of ionic compounds, that's somewhat new. It was in your notes May 6th. I did not teach it. I'm going to teach it today, but it's right here. This, I don't know whose book that is out of. It might be yours, might be some other book. But I'm going to talk about this. How do you get the formula? How do you get the subscripts? It's called the crisscross method. Then below that, we see the polyatomic ions that I've asked you to learn. Here in handwriting is how to turn one of those polyatomic ions into 4 times the amount of information. If you learn the ATEs, the ATE ending, if you learn the ion that ends in ATE, I will show you, or you can read right here how to convert that information into 4 times the amount of information. In other words, from the ATE ion, you get the IDE ion, which you already know from monatomic ions. You get the ITE ion, the hypoite ion, and the per8 ion. It does it say per8 there? I think it does. No, it doesn't. I don't have the per8. I wonder why. Down here, this is a deeper explanation of this. Down here in red is a deeper explanation of how to get the other ions from the ATE ion. Now, this periodic table, I think I invented it. Not the periodic table, this periodic table. It's the periodic table of bonding. The periodic table of bonding. I think I invented it. I think I invented this trend. I didn't invent the trend. I think I invented the presentation of the trend. The fact that there are 4 ways to present 4 carbons, 4 bonds, 3 ways to present nitrogens, 3 bonds, 2 ways to present oxygens, 2 bonds, 1 way to present fluorines, 1 bond, and no way to present neon's bonds because neon doesn't make any bonds. So I'll call that a Betalism until somebody proves me wrong. We're not going to get this today, but you should know it. It's not that complicated. All right. You need to know how to use this flow chart to make the decision how to name a compound either as an ionic or a covalent. Then there's the opposite, how to get a formula from a name. How to get the formula from the name. Then there's covalent naming, covalent nomenclature. It's different. Covalent bonded compounds have different naming system than ionic. You'll see these prefixes in covalence. Mono, di, like carbon dioxide, that's a covalent molecule. You never see these with ionic compounds. So there's how to name acids. That's not going to be on, I don't believe that, unless that's in chapter 7, that won't be on the quiz, but it's there for you to learn. Let's get started. I'm going to go all the way up to here, and I'm going to start with chemical reactions. Now I'm going to give you some notes that aren't up there yet. This is going to be new information, brand new. It's not in any of your notes. So chemical reactions, I'm going to give you these notes because they should be fresh on your mind based on our recent presentations. Look at that. That's amazing. Huh? Chemical reactions. Now we learned through presentations that there were 5 basic chemical reactions. I'm going to back that up a little bit, and I'm going to tell you there are really 2 basic chemical reactions. 4 of the chemical reactions that you learned through the skits are all grouped together under one major category. And then one of the chemical reactions, one of the 5, is a separate kind of chemical reaction altogether. It's very unique. So the first reaction that I'm going to talk to you about, this is a major category, oxidation / or hyphen reduction. It's just called oxidation reduction. And I'll say versus double replacement. When you look at what goes on with electrons, you will realize that double replacement reaction is very different from oxidation reduction reactions. I'm going to explain what this is in a minute, but you might I'm going to put above that an abbreviation and give you a little hint. So oxidation reduction, here it is. Change in electron structure. Now, why is that big news? Because you probably or may have heard me say at some point from the beginning of the school year to today that chemistry, that's what chemistry is. Chemistry is when you change the valence electron structure of an atom. And I have said that if you do not change the valence electron structure of an atom, you have not done chemistry with the atom. Typically, it's considered a physical change. For example, if you take this and put it in water, now this is a solid, it's a salt. If you pour it in water and stir it, it disappears. It seems to disappear. It's not, it's still there. You can taste it and see that it's still there. Salt water. What happens is you're dropping into the water an ionic compound, sodium chloride or potassium chloride, I'm not sure what that one is. And as it gets into the water, the polarity of water, H2O, hydrogens tend to be positive, oxygen tends to be negative based on the electronegativity. It's a polar covalent bond, and the molecule is not symmetrical in all directions. Therefore, the molecule itself is polar. It actually pulls apart the ions of sodium and chlorine, or other salts will do the same thing, pull apart. But we don't call that a chemical reaction. We call it a physical reaction. And the reason why it's considered a physical reaction is because when they are together, they're Na plus, sodium plus, and Cl minus. The only thing different is the geography. The only thing different is the geometry, the spatial distance of the ions. You know, who sets an arbitrary distance at which point they're no longer, you know, they're still ions, whether they're close or far apart. So we call that a physical change. Just a change in the location of the ions with respect to each other. When you look at double replacement reactions, there's no change in the electron structure. The only change is in the spatial separation of two ions. Instead of going apart, they attract each other and form a new compound, but they don't change their electron structure. And we call it a chemical reaction because the product is different from what was put into the water. But if you think about it, and I've imagined this as a double replacement reaction. Let's say you have a long aquarium full of water, and you've got a glass divider between the two halves of the aquarium. That's a glass divider that's full of water. And on one side, you put sodium chloride, which I just talked about. And as you put it into the water will shred it apart. The water literally tractor beams it apart. If you're a sci-fi person, you know what the tractor beam is. You end up with Na plus and you have Cl minus, stabilized by the polarized water. Over on the other side, let's put silver nitrate.
So the water just like pulls apart the bond?
The water literally, imagine if you want to think of sodium and chloride, let's say they're wrestling. They're really good friends and they're wrestling, but they're at school wrestling, and the administration might think they're fighting and give them referrals and you know, suspend them. So all of their friends jump on them and pull them apart. And that's what water does. Water does that to salts. Not all salts, but many salts. I'll give you an example. Actually, hang in there. I got a physical example I will show you. This is a fossil seashell. It's embedded in limestone. Limestone is calcium carbonate. Well, calcium carbonate is a salt. Mollusks breathe in, you know, they have metabolism. They're breathing in, and they get carbon dioxide both from their own metabolism and from the ocean water around them. And they metabolically produce from the carbon dioxide, they produce calcium carbonate to build a shell or a house around themselves, whether it be a snail shell, a clam shell, or a coral a coral rock, coral branches, like a tree. That is a salt. And water is not capable of pulling calcium away from carbonate. So many salts, when salts dissolve in water, it's like the water molecules are like your friends pulling you apart from wrestling with your other friend, and they're afraid you're going to get a referral for fighting. So they jump in and they pull you apart. You're like, we're just playing. They're like, yeah, but don't do it here. Okay, you'll get suspended. Water does that to sodium chloride. Water does that to silver nitrate. Water does that to many salts. Most salts will dissolve in water because water molecules, being polar, a water molecule looks like this. And if you look at the electronegativities, the delta En between the hydrogen, and the oxygen, the direction that the electrons get pulled is towards the oxygen. So we make a little plus sign. It looks like a religious symbol almost. We make a plus sign on the back of that arrow to show that the back side of that arrow is positive, the front side is negative, and we get this net polarity where the hydrogens are plus, the oxygen is minus. And so what actually happens is when you put sodium, which is positive, and chlorine, which is negative, what ends up happening is surrounding the sodium, you get this. The hydrogen ears stay away from sodium while the oxygen face goes towards sodium. Like so. And then the opposite happens around the chlorine. The plus ears are attracted to the negative of the chlorine. And they start wedging in between here and they break up the sodium and the chlorine. And that's called dissolution. Solvation. Things dissolve. Solvation is when things dissolve. So that's what's going on over here, and that's what goes on over here. When you drop silver nitrate in, the water does the same thing. You get Ag plus and NO3 minus. Now, here's silver and here's chloride. They're only separated right now by space and a glass divider. Now let's say I reach in here and I grab the divider and I pull the divider out. When I pull the divider out, for a brief moment, the separation between silver and chloride continues. But at that moment, you could argue they're just two ions floating around near each other. But that's not what it stays. They suddenly feel each other and begin pulling towards each other more strongly than the water. The attraction between silver and chloride is actually stronger than the attraction of water for them. So they end up sticking together and excluding water. They squeeze the water out of this area. And water can't get between silver and chlorine. So you end up with AgCl, and we put a little parentheses S here to represent solid. And this sinks down. It's called precipitation. Just like when it rains outside, water's falling out of the sky, they call that precipitation. Well, they call this precipitation because it sinks down. Or I like to say it settles down. And here's why. This is a double replacement reaction. I'm comparing oxidation reduction reactions to double replacement. I like a little analogy here. This is, you can tell why I gave you the human relationship sketch. Here's the story. I'll tell you the story. This is the way I see it. Sodium and chlorine. They're a couple, but they're not a couple. You see, sodium is what we would call a player for life. Sodium will never be in a committed relationship. I don't know why Brian's nodding his head yes like that. Brian, is there something that you want to say? No? Okay. Yeah, so sodium is a player for life. Sodium will never settle down in a solid relationship. You get the wordplay there? Settle down, solid relationship. It's intentional. Sodium is not like that. Sodium is the Lone Ranger, man. Sodium drinks alone, as they say. Sodium is friends with chlorine, so sodium's like the wingman. Sodium is like the escort. So it's like, yeah, I'll drive you to Club H2O. Get it? Like that? Club H2O. That sounds like a nice place to go, right? Let's go to Club H2O on South Beach tonight. It's Friday. So sodium drives chlorine to Club H2O, and they say, let's get in. So they get in, and of course, as soon as they get out on the dance floor, sodium's doing his own thing. He's like separating himself from chlorine. He's not going to hang around chlorine that much. That's all right. Chlorine's not. Some people think chlorine is a player for life. A lot of ions, they think chlorine is a player for life. They get near chlorine and they want to hook up, and chlorine's like, they're like, oh, their feelings get hurt. So they say, oh, chlorine, you got commitment issues. Well, guess what? Chlorine has no commitment issues at all. chlorine is waiting for a better class of ion. Ooh, that hurts. That hurts some of those cations, you know, they just can't handle it. Well, silver nitrate, they're a couple, but they're not a couple because nitrate is like sodium. Nitrate is a player for life. Nitrate does not settle down. Nitrate just wants to dance alone. Yeah, man, I'll drive you to the club H2O, but guess what? Don't crowd me. Don't get in my space. When we get there, you better go find some friends because I don't need to be, you know, tied down. So that's nitrate. They show up at club H2O, and silver sees chlorine, chlorine sees silver, and that's it. They're drawn magnetically to each other. They feel each other. They attract each other. They feel more strongly attracted to each other than all of the pull and tugs of any other ions or even water. And at some point, they find each other. It's almost instantaneous, by the way. You do this in water. I don't think we can do this because I mean, I can do it as a demo. We will do a lab day. We'll probably do a couple lab days where we have all of the chemical reactions, all 5 chemical reactions demonstrated. I'll come up with one you can do at home that will parallel this, but I don't think too many of you have silver nitrate laying around. It's expensive. Silver nitrate. The silver part gets you. All right. So, but silver sees chlorine, chlorine sees silver. They like rush towards each other. It's instantaneous. You'll see the whole solution. As soon as you pull that divider, the whole solution is white. And then if you let it sit there long enough, the white settles down and it forms a layer on the bottom, and then it's clear up top again. And up top, you got sodium and nitrate. And a lot of people say, well, do they form a compound? No, it looks like it on paper. If you see if you see sodium and nitrate at the club, they're dancing together, but they're not a thing. They're not a thing. They don't stick. There is one way to make them stick. And it's the same way that I would have a chance with Kim Kardashian. I have a chance with Kim Kardashian. You know that? There's only one chance, though. If I was on an airplane flying across the Pacific Ocean and she would be up in first class, never, you know, she'd have bodyguards and everything, probably on her own jet by now. But anyway, let's just say she's up there. And all of a sudden, did you guys ever see Survivor, the TV show Survivor?
No.
Great series, great series. It goes into a dive and it crashes into the Pacific Ocean. If I woke up trapped on a deserted island with Kim Kardashian, she'd probably need a little help. She'd probably need a little company. If we were the only 2 people on the island, she'd probably, after a day of trying to ignore me and trying to find other means off the island, at some point she would have to just break down and surrender and say, okay, Sean, because that's my name, Sean. Okay, Sean, I need some help. She probably wouldn't say it like that. She'd probably say, I'll let you be near me. You know, whatever. Hey, man, I could start a fire. I could catch fish. Or what is the song? I can run a trout line. I could skin a buck. I can run a trout line. A country boy can't survive, right? So that's the only chance in hell I would ever have with Kim Kardashian, is if the 2 of us got stuck on a deserted island. And that's how you make sodium and nitrate settle down. You put them in club H2O and you evaporate the water. In other words, you get rid of the water so they have to get closer and closer. It's like putting them on a deserted island. As you evaporate the water, the sodium and nitrate, they're looking around, they're like, I got nowhere to go. And then, of course, when you've evaporated all the water, the positive and negative ions will then have to stick to each other because they got nowhere else to go. It's like being on the deserted island. Kim Kardashian, she's got nowhere else to go. She's going to stick around you. You offer the protection, the food, whatever, the company, somebody that she can brag to, right? Right? No wonder Kanye went crazy. All right. Did I say that out loud? Okay. So there's my story about double replacement. If you look at the electron charges, they don't change. Silver is still +1, chlorine is still -1. A double replacement reaction, if you really think about it, there's no change in the electron structure. It's very different from oxidation reduction. Very different. Club H2O, man, that's where it happened. All right. These involve change in electron structure. I'm going to give you something called a mnemonic. Mnemonic is a trick that you use to memorize things, like Roy G. Biv or SOHCAHTOA. Remember SOHCAHTOA? No? Does anybody?
Yes, I remember it.
Thank you. Thank you. Sine, cosine, tangent, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Here I am, 56 years old. I still remember my 10th grade trigonometry class. All right. Because it's a mnemonic, it's a memory device. Here's the memory device for you guys. Oil rig. Notice I put oil over oxidation and rig over reduction. They both start with the letter O for a reason. Oil rig. You guys know what an oil rig is. An oil rig in Texas used to be a tall tower like this, and they would run a drill down into the earth. When they drilled into the earth and they hit an oil reserve, they hit a pocket of oil. Whoops. When you hit a pocket of oil down here, it comes splurting out. A gusher. We hit a gusher. You'd ever see that in a cartoon or something? All right. That's an oil rig. If you go out to Texas now or Colorado or somewhere and look at oil rigs now, they don't look like that because we've tapped all the easy oil. There's very little oil that sits on the surface like that that's under high pressure. They found all of that. So now what we have to do is frack. You know, we do the fracking. Oil rigs now look kind of like this. And they have this structure that's on a pivot. And it's got a pipe there and a pipe there. And it goes back and forth and just rocks up and down. And these things pump the oil because it's not under pressure anymore. We got all the easy oil out of the ground. Now we're pumping oil out of the ground. So anyway, oil rig. They're both oil rigs. Just two different kinds of oil rigs. Oil rig. Where is it? Floating, roll up. There we go, roll down. Jesus. Here's what oil rig stands for. Oxidation. When you see this, you're going to be, oh, that's amazing. Oxidation is loss of electron. Remember I said oxidation reduction. Redox reactions are a change in the electron structure. Well, in a change of an electron structure, somebody gains electrons, somebody loses electrons. Remember, elements are trying to get to the octet. Some of them get there easiest by gaining electrons. Some get there easiest by losing electrons. Those that lose electrons are said to be oxidized. You've probably heard that word, rust, oxidation. When you cut an apple, it turns brown. It's oxidized. You can buy stuff to sprinkle on it that will make it not oxidized. If you have silverware that you bring out to special dinners like weddings or quinceañeras or Christmas or Hanukkah or Thanksgiving, and you bring it out and it's gray and your mother gives you some polish and you have to rub the silverware to get the gray off and make it bright and shiny. You're getting the oxidation off of it. If you've ever been to New York City and looked at the Statue of Liberty, it's made out of copper, but we think of copper as being yellow-orange, not green. Statue of Liberty is green because the copper has oxidized. It's reacted with oxygen. The copper has lost its electrons. Oxidation is loss of electrons. Reduction. Well, if somebody loses an electron, somebody else has to do what?
Gain electrons.
Gain electrons. Thank you for paying attention. Somebody else has to gain. Reduction is gain. Now, if you think about it, it makes sense. When you gain an electron, your charge goes more negative. More negative is lower. So you're reduced. Your charge is reduced. We think of reduction as going towards zero, but you can go below zero. And as you go -1, -2, -3, you're being more and more reduced as you gain more and more electrons. So reduction is gain of electrons. So in a chemical reaction where two atoms come into contact with each other, and one gains the electron and one loses the electron, one goes positive, one goes negative. The one that gains the electron is more negative, so we say it's reduced. The one that loses the electron, because the electrons are negative, goes more positive, we say that's oxidized. Typically, oxygen was one of the most plentiful elements on the surface of the earth. In the atmosphere, it exists as O2. When it comes into contact with things, usually it looks at itself, O2, to oxygen, it says oxygen. Yeah, oxygen. Let's go get electrons from those guys so we can separate finally. You know, it's like two conjoined twins. You know, they want to be separated and then have their own independent lives. Well, that's oxygen. O2. It says, look, it looks at itself, it says, hey, let's get away from each other and we'll go take electrons from that other substance. And then we can be separate from each other. So they don't need each other anymore. Okay. So oxygen reacts practically with everything. That's why the Statue of Liberty is green. That's why your car turns orange rusty. That's why your apples and bananas turn brown when you cut them. That's why your silverware tarnishes. That's why your aluminum screens and your aluminum frames of your windows get chalky. You touch them and you're like, oh, what is that? You know, it's oxidation. Oxidation. It's why red bumper stickers eventually turn white. You know, all kinds of things like that are reacting with the oxygen that's in the air. There's only one element more electronegative than oxygen. Does anyone know what that element is?
No.
You'd have to look at a periodic table and know the trend of oxidation or electron numbers, electronegativity. The trend in electronegativity is towards the top right. What's to the top or right of oxygen?
Helium?
Well, helium is placed top right, but you got to remember helium is also a noble gas. It doesn't want any electrons. That was the trick question on the quiz. It has an electronegativity of 0, basically. So you don't want to say helium. There's only one other element that's either above or to the right of oxygen.
Fluorine?
Fluorine. Good thing for us, fluorine is not running around in the atmosphere. There would be no life on Earth. If fluorine, or if there was life on Earth, if fluorine was our dominant gas, it would probably be very different than what we're used to. So oxygen is the dominant one, it's 20% of the atmosphere. It's probably 40% of soil. How? Well, water vapor, titanium dioxide, silicon dioxide, quartz sand, carbonate, it's in carbonaceous limestone, CO3. Oxygen in our environment, oxygen is one of the most dominant elements on the surface of the Earth, and it reacts with everything. So that's why, no big surprise then, that's why the process of losing electrons is referred to as oxidation, because oxygen was the very first and very most popular agent for stripping electrons away from something. It's one of the most reactive elements on the surface of the Earth, oxygen. They say oxygen is a poison, it's killing us. We have to breathe it for metabolism, but every time it comes into contact with anything in our cells, it oxidizes, and their cells have to have all these toolkits of rescue and survival to repair any oxidation that oxygen is doing outside of the venue that it's supposed to do metabolism. And they think it's a major part of aging. These wrinkles you see on me probably have to do with either sunlight, yes, maybe oxygen. Oxygen, when it comes into contact with DNA, strips electrons away from DNA, and the DNA has to either be repaired or the body has to tell the cell, hey, cell, bye-bye. Cellular apoptosis. Get out of here. And that's when wrinkles happen. All right. So oxidation is loss of electrons, reduction is gain. Synthesis. Let's talk about synthesis. The generic form of synthesis is A plus B yields what? AB. That would be synthesis. You guys need to memorize this by next Thursday. No, you don't. You don't. This is not until the next quiz, but I'm still teaching it because I'm going to use it here in a second. A plus B yield AB, synthesis. You take two simple things, combine them, two or more simple things, because you could have A plus B plus C yields ABC, or A plus B plus C yields, no, that wouldn't, okay, there you go. A plus B plus C would be ABC. Synthesis. A specific example of synthesis that I'm going to use to make a point, H2 plus O2 yields H2O. Hydrogen gas, what's that?
What happened to the other oxygen?
That's a great question. I'm so glad you asked it. I'm going to teach you how to balance the mass, but not yet, because there is a law of conservation of mass that says you cannot destroy matter. So if you have two oxygens on the left, you better have two on the right. Now we have 4 hydrogens on the right, so we better have 4 hydrogens on the left. And then now it's balanced. Okay, that's a balanced chemical equation. I will teach you how to do that in 2 weeks. Just in time to get out of school, right? All right. This is in your notes from May 6th. I think it was May 6th. If it wasn't May 6th, it was the first. No, it wasn't May 6th. This was the first day that we did presentations, May 10th, Monday. I put this in your notes as an example of synthesis. It's an important reaction. Not only is it important because it tells us how we get water from space, it's also important because it's probably going to be the source of electric power. It already is the source of electric power on the space station, and in all the earlier spacecraft that we had. If you take a tank of hydrogen and a tank of oxygen and slowly combine them in the presence of 2 electrodes, you get water plus electricity. The electricity comes as the hydrogens get oxidized. The electrons travel from the hydrogen to the oxygen through the wire, which produces electrical work. So you get your lights on, you get your radio on, you get your computer working, and your product is water to drink. It's fantastic. You can use sunlight. You can use sunlight through a photocell to split. In the space stations, they split the urine. They collect the urine, and they run this backwards. And they produce hydrogen and oxygen, which you can then use as fuel and produce electricity all over again. So it's a nice little cycle. Yes, they do. They do recycle urine on the space station.
So they use their pee to power the ship?
Well, they use their pee they use sunlight and pee to split apart the water to make hydrogen and oxygen. And then they recombine the hydrogen and oxygen to make electricity and water to drink. Yes. indirectly. So I bring this equation up to you, this reaction up to you, to tell you very clearly that this is synthesis. We have a name for this reaction where you combine a pure element and a pure element to make a more complicated compound. It's called synthesis. And I tell you this specifically, this is not combustion. It is incorrectly identified in some books as combustion or on some websites as combustion. Why? Because a flame is produced. If you want to see that flame, Google Hindenburg Disaster. You may already know this. There's video of one of the early Zeppelins, dirigibles, or whatever you call them, the balloons that carried people back and forth across the Atlantic Ocean in the early 1900s, very early 1900s. They were filled with hydrogen gas because the hydrogen gas is very buoyant. It's 14 times lighter than air. So it can carry 14 times, it's basically its volume of mass. So when it combines with oxygen rapidly, it releases a tremendous amount of energy known as flames. It explodes. Heat, light given off, there are flames visible. The Hindenburg disaster just happened. The thing caught fire in the air. Hundreds of people crashed down to the ground, some of them on fire, over 100 people died. Terrible, but it's not combustion. A flame is not combustion. Combustion is a different reaction. I'm going to give you a definition for combustion in a minute.
So are these all under the oxidation reduction category?
Yes, all of these on the screen right now are oxidation reduction. Look, the charge here on hydrogen is 0. The charge here on oxygen is 0. When they combine, because oxygen is more electronegative, it goes -2 and hydrogen goes +1. So there's been an exchange of electrons. We'll talk about that more. There's another reaction that I want to tell you. Mg plus O2 yields MgO. And you can ask the same question, Genevieve.
Where did the two go?
Where did the other oxygen go? It didn't go anywhere. It's there. We didn't balance the equation. Now it's balanced. So same thing. Magnesium joins with oxygen to form magnesium oxide. We already have a name for this reaction. It's called synthesis. A plus B yields AB. Why do we need to invent a new category for that? Just because it's exothermic. Lots of reactions are exothermic, even in the other category. There are exothermic decompositions. There are exothermic single replacements. We don't call those combustion. So I'm going to tell you what combustion is in a minute, but I'm going to insist that these are not combustion, and I'm going to give you the definition for combustion in a minute. Decomposition is easy. It's the opposite of synthesis, isn't it? Decomposition is the opposite of synthesis. AB yields A plus B. Here's an example. Sodium hydrogen carbonate. You could do a reaction in which sodium plus hydrogen. Oh no, let me back that up. Let's make that water. Let's make that water. Plus water plus carbon dioxide are formed. Yes, where did that extra hydrogen come from? We can balance that, but it'll take longer than I have time to do right now. We have a compound that we treat, maybe by heat, maybe by electricity. And from that, we get pure sodium. We get pure sodium. We get water, and we get carbon dioxide. So, decomposition, it's the opposite of synthesis. Does anybody need any further explanation about that? Here, the sodium goes from +1 to 0. So there's been, sodium has received an electron.
After it's balanced, how do you know what makes it up? Because I wouldn't be able to.
How do you know what?
How do you know what makes up? How do you know what it breaks into from? Even though
you don't always know until you get more experience. So if I gave you a quiz question and asked you what the decomposition product of this would be, I would give you, it would be multiple choice. And, one of those would be this, NaH, carbon, and oxygen. It'd probably be H2 and O2. And that would be one of your choices. So that would be your decomp choice. You don't have enough experience to know this yet. But you do know that when you decompose something, it's breaking down to its basic elements, or simpler substances, is the correct way of saying it. Okay? Now,
so which one would be the right? Are they both right?
Yeah, they're both right. If you raise the temperature high enough, like if you put any compound, if you fly any compound into the sun, let's say we have an entire space projectile, some kind of probe that we send into the sun, which we've done, it will work for about 5 minutes in the upper atmosphere of the sun before it completely melts and falls apart. And then it won't just stop there. You're talking about 20,000 degrees Celsius. It's going to then destroy every compound that was there. And it will turn every compound into the individual elements, just like that. But it'll even go further than that. There won't even be diatomic molecules. They'll just be, they won't even be negative. They won't even be neutral atoms. They're going to be ionized. All the electrons will get stripped off. So you'll have plasma. You'll have a bunch of positive ions and a whole bunch of electrons free. And those electrons will continuously be recaptured by the positive ions, which is where the light from the sun comes from. Because whenever an electron is captured back by the atom, it releases its potential energy as light, radiant energy. That's why the sun is giving off light. Okay, I'm going to do combustion now, separate. Combustion is completely separate. Well, I'm going to treat combustion now. I'm going to give you a definition for combustion. So I don't know if this was the class, but one of the classes gave a pretty good definition for combustion. So you're going to recognize this if that was you. In parentheses, I'll put rapid, because you can argue that right now our bodies are using combustion slowly to fuel us. Because we have a form of hydrocarbons that we use for fuel, but our hydrocarbons are edible. We can't eat oil. We can, but it's not a pretty sight afterwards. We don't eat oil, but we do. There are oils that we can eat, vegetable oil, olive oil. Those oils are not called hydrocarbons. They're called carbohydrates, because they also have oxygens in them. So edible, consumable hydrocarbons are often called carbohydrates. It's the same letter, it's just backwards. So combustion, and the reason I bring that up is, in a sense, our body is undergoing combustion slowly using enzymes, catalysts, enzymes, to do the combustion slowly at lower temperatures. But I put rapid in parentheses. The rapid oxidation, remember oxidation, traditionally combining it with oxygen so that the thing that's being combusted is losing electrons, whereas the oxygen is gaining electrons. Oxidation, the rapid oxidation of hydrocarbons, asterisk up here, hydrocarbons, to produce water and carbon dioxide. This is very important that you understand what the definition is here. This is kind of an old school definition. I kick against the tendency to include magnesium and hydrogen oxidation into combustion, because just because they give off a flame and heat, just because they're exothermic, there are other exothermic reactions, but we already have the category synthesis that adequately describes them. So I'm going to reserve combustion for hydrocarbons with a product of water and carbon dioxide. If you look at synthesis, you only get one product. When you do synthesis, you get one complex compound from two simpler substances. Combustion, that's not the case. They might be simpler. No, they are simpler. The products are often, carbon dioxide and water are often more simple than the fuel. So it is a necessary category of redox reactions to have combustion separate from synthesis. And I reserve it for hydrocarbons. So here's the generic format, CnHm. Put that asterisk up here, same as that single asterisk there, plus O2 yields, and Genevieve, I'm not going to balance it because we have N and M there, and it turned out to be a very algebraically ugly equation. I'm just going to say you get this. It's not balanced. You could do the balancing, but that's it. These four things are required in the reaction for it to be classified as combustion. Not Mg plus O2, not H2 plus O2. Those are synthesis reactions. And I'm going to put a double asterisk here, and I'm going to explain my asterisk and my double asterisk right here. In order to explain my single asterisk on hydrocarbon, I'm going to ask you this. What was everybody's impression of hydrocarbon before I mentioned that edible hydrocarbons are called carbohydrates? What was your impression of hydrocarbons? Where do they come from? Where do internal combustion engines get their hydrocarbons for fuel?
Oil?
What?
Oil, I don't know.
Yeah, oil. Where does that come from?
The earth.
Where did that come from before? I mean, why is it in the earth?
I don't know.
Do you have a nickname or a synonym for oil that comes out of the earth that's used as fuel?
Yes.
What's the nickname?
Yeah, what Christine said.
What'd she say?
I said fossil fuels.
Fossil fuels, exactly. Fossil fuels. Most historically were fossil fuels. Why are they called fossils? Why is it a fossil? Where did it come from? What are
The
fossils?
remains of dead things.
Yes, remains of dead things that have been preserved. So, for example, coal, I think, comes from plants that have been squeezed under high temperature and pressure in the earth into coal. And oil, if I'm not mistaken, comes from either microorganisms or dinosaurs or something like that that died in big piles that got compressed, and heat and temperature cooked it into oil. But these were living things. And in order to be a living thing, you can't just be carbon and hydrogen. That would just be a lump of wax. Wax is not that exciting, has no personality, doesn't go skating, doesn't whatever, you know? So it was living because it had the 5 basic characteristics that you learn about in biology, which some of which were metabolism, right? Reproduction, DNA. To be considered life on Earth, you have to have the ability to reproduce using DNA. And then there was one where you keep yourself separate from your environment. I forget what the name of that one is. You separate from your environment. What? Something like that. You're able to distinguish yourself from you don't blend into your environment. You don't melt into your environment. Anyway, but the 2 that I needed, I already said, DNA for reproduction and cellular. Oh, cellular. They gotta have cells. They gotta be based on cells. Well, cells operate as machines because they do chemical reactions and they have equipment. They actually have little tools in them. Endoplasmic reticulum, mitochondria, organelles. They do work. Muscle cells actually move. They contract by jacking these proteins shorter. Well, proteins are made up of amino acids, 20 amino acids. Amino acids contain nitrogen, sulfur, phosphorus. The cytoplasm contains potassium salts, calcium salts. They have to pump these ions across semi-permeable membranes to make signals go down the line, nerve signals, for example. They have to have salt. So in other words, living things that got heated up and compressed underneath the earth, whether they be plant or animal, do not only contain carbons and hydrogens. There's a lot of other elements. C. Hopkins Cafe, mighty good but salty. Carbon, hydrogen, oxygen, phosphorus, potassium, iodine, nitrogen, sulfur, magnesium, mighty good but salty. Sodium and chloride. They're all there, not just carbon and hydrogen. Just because we're organic doesn't mean we're only organic. We have a lot of inorganic material in us that allow us to operate. So these things contain sulfur, phosphorus, nitrogen, potassium, chlorine, sodium, etc. So when you burn fossil fuel, you do not just get carbon dioxide and water. That would be great if that's all we got. I think that's why they're switching over to a lot of these natural gas buses and things, because they produce less sulfur dioxide, less nitrous dioxide, nitrogen dioxide. These things, when these things oxidize in the same environment that the carbon's oxidizing, they produce nasty sulfur dioxide, phosphorus trioxide, nitrogen dioxide. These things then dissolve in rain and produce sulfuric acid, phosphoric acid, nitric acid. So, and this stuff, not only does it produce gases that dissolve in rainwater that produce really bad acid rain. All rain is acid rain, by the way. Carbon dioxide, when it dissolves, which is a natural component in the atmosphere, dissolves in water to form carbonic acid, H2CO3. That's an acid. All rainwater is naturally low pH, but these guys are very strong acids. When they get into water, they will form strong acids that then eat up both natural and human beautiful rock sculptures, whether it be natural rock sculptures in the Grand Canyon or the great, like Dakotas, but it also eats up Michelangelo's statues and whatnot in Rome. So we're very careful now. We understand fossil fuel, can produce bad byproducts in addition to carbon dioxide, which is contributing to global warming. My Jeep, I have a Jeep Grand Cherokee out in the parking lot. It's got the bicycle on the back today, if you saw it. It has a Mercedes 3.0 diesel in it. And when I change the oil on that thing, it costs almost $100. I do it myself. I have to use a synthetic oil that's made from individually linking methane molecules together in a chemical reaction to produce synthetic oil so that it doesn't have all of these contaminants, because Mercedes doesn't want to spit out smoke from their engine. Because they know if they do that, they will lose market. Because people don't want to see smoke coming out of engines. Smoke comes out when you have these things in the fuel, because these things oxidize and they have color. You see brown smog in the air from the sulfur and the nitrogen oxides. You see smoke because potassium, chlorine, and sodium make particulate matter. Particulate matter, ash. So that's why that single asterisk is there. There are plenty of combustion reactions that are not pure. The double over there refers to this. The double is to signify that you can actually have incomplete combustion. So complete combustion, you produce CO2. Let me give you a warning. We're getting ready to start hurricane season. 2 weeks we'll be going into hurricane season. We're going to get a hurricane at some point this year, if not this year, next year, where we lose power for a few days, maybe a week, maybe 2 weeks. Hi, what's up? Oh, hey, Luigi. I was just complimenting you earlier on your nursing role there. How well you came out of the womb and how well you fit in Matthew's. But let me finish this about hurricane season. We're going to lose electricity. And there are idiots that live in Miami and Alabama, in Georgia, in South Carolina. Every hurricane, they say, hey, let's get the generator in the house so people don't steal it. Good idea. Then they say, hey, let's sleep at night with air conditioning on by running the generator in the house. Well, bad idea. Same thing with running the car in the garage, or the same thing with bringing the barbecue in to barbecue during the hurricane. Because those combusting items, those items that run on combustion, will draw oxygen out of the atmosphere, which you need to breathe, and they need for combustion. And as they run out of oxygen, they begin to ration the oxygen in this reaction, and they no longer put 2 oxygens on every carbon. They begin to put 1 oxygen. Incomplete puts 1 oxygen. Does anybody know the name of the carbon product that only has 1 oxygen?
Carbon monoxide.
Carbon monoxide, CO, will kill you because it sticks to your hemoglobin so powerfully that your body cannot remove it. You literally choke to death, but you don't know it because you get sleepy before you choke. And you say, hey guys, wake me up when you're done barbecuing. And you wake up dead. So don't do it. Don't let your family bring the barbecue or the generator or the car and run it in the house. Have a great weekend, guys. Study the notes. I'll see you on Tuesday.
Hi, Miss Evans.